This is a continuation of video 5a. We will be discussing more about the Bohr's model of hydrogen atom. Before discussing the postulates of Bohr's model of hydrogen atom, let us recap the important postulates of Rutherford's model and learn about any limitations of the model in light of new experimental data related to the emission spectrum of hydrogen atom. According to Rutherford's model of atom, the electrons revolve around the nucleus like planets revolve around the sun. And that is why his model was called as planetary model. For the planetary system, the centripetal force is provided by the gravitational force of attraction between the sun and the planets. However, for an atom, the centripetal force is provided by the electrostatic force of attraction between the electrons and nucleus. There were two big limitations or drawbacks of Rutherford's model of atom. According to classical laws of physics, a charged particle like an electron accelerating around the nucleus continuously loses energy in the form of electromagnetic radiation. As a result, the electron would spiral down into the nucleus, leading to the destruction of all atoms. However, the world as we see it is made up of atoms that do not collapse spontaneously. So, Rutherford's model could not explain the stability of atoms. That is, why are atoms stable? The second limitation is, if the spiraling electron continuously loses energy without any breaks, they should emit a continuous spectrum. However, as we discussed earlier, atomic emission spectrum is a discontinuous spectrum with bright lines on a dark background. Therefore, Rutherford's model of atom, which is based on classical laws of physics, could not explain the experimental observations such as the stability of the atom and the line spectrum of an atom. In the year 1913, after working in Rutherford's lab for a considerable amount of time, Niels Bohr proposed his model of atom. He combined the laws of classical physics with a few quantum concepts and some clever assumptions to propose his model of atom. We are going to discuss the postulates of Bohr's model of hydrogen atom in the next few slides. The first postulate he proposed was, electrons move around the nucleus in circular paths of fixed radius and energy. Because these orbits have fixed radius and energy, he called them stationary states. The word fixed is important here. Rutherford's model talked about the electrons revolving around the nucleus but not about the orbits having fixed radius. Let me explain what I mean by fixed paths. For example, if we have to place a ball on a ramp, we can place it at any altitude we want to. However, if we are placing it on a stairs, we can either place it on step 1 or step 2 or step 3 and so on. We cannot place it between the step 3 and step 4 or any other combination of steps. Similarly, an electron can either stay in orbit 1 or orbit 2, but it cannot stay between the two orbits. The existence of these paths with fixed energy and radius is an important distinction from the previous model of the atom. As we will discuss in the next few slides, this idea of orbits with fixed radius and energies explained the atomic emission spectrum of hydrogen atom. The second postulate of the Bohr's atomic model is, the electron revolves around the nucleus only in those specified orbits in which the angular momentum of the electron is an integral multiple of a constant value h over 2 pi. The angular momentum of an electron of mass m moving with a velocity v in a circular path of radius r is given by the formula mvr. According to Niels Bohr, mvr is equal to nh over 2 pi, where n is any integer value representing the orbit number and h is Planck's constant. Let me break this down further. The first postulate says that the electron revolves in orbits with fixed radius. These orbits are not only fixed, but the possible values of this radius are also restricted. That is, the electrons cannot revolve in orbits with any radius they want to. They can only have certain discrete values of radius in which the angular momentum of the electron is an integral multiple of h over 2 pi. This is called as quantization of angular momentum. Again, let us go back to our ramp versus stair analogy and understand what this postulate actually means. What we are saying now is that the steps can only be at certain predetermined altitude based on some formula. Next postulate. Based on the quantization of angular momentum, classical principles of electrostatic attraction, circular motion, and a few other assumptions, Niels Bohr calculated the radius of each orbit of the hydrogen atom. According to Niels Bohr, the radius of nth orbit of a hydrogen atom Rn is equal to n square over z times 52.9 picometers, where n is equal to the orbit number, which can have values 1, 2, 3 and so on, and z is equal to the atomic number. Because of the type of assumptions Niels Bohr made when he derived this formula, it is applicable for an atom or ion with only one electron inside. We call these monoelectronic species. As we know, the only atom with one electron in it is hydrogen, for which Z is equal to 1. So we can use this formula for calculating the radius of orbits inside the hydrogen atom. For helium, we have 2 protons and 2 electrons in it. So the above formula is not applicable for helium atom. However, if we remove one electron from helium, we get a monopositive helium ion, He+, which has only one electron. So the formula can be applied to calculate the radius of He+ ions. The Z value for He+ is equal to 2. Similarly, for lithium atom with Z is equal to 3, it has 3 protons and 3 electrons. However, if we remove 2 electrons from it, we get lithium 2+ ions, and the formula can be applicable for lithium 2+ ions. Another important thing to take note here is that the spacing between the orbits is not equal. As the n value increases, the radius increases by n squared times. Therefore, we can say as the n increases, the spacing between the orbits increases. That is, spacing between orbit 1 and 2 is less than that of spacing between orbit 2 and 3, and so on. Let us do an example problem. Calculate the radius of 5th orbit of beryllium 3+ ion. Pause the video here and try to answer this question. First, we will check if the formula given by Niels Bohr is applicable to beryllium 3+ ion or not. Atomic number of beryllium is 4, so it has 4 protons and 4 electrons. Beryllium 3+ means it has 3 more protons than the number of electrons, which means we need to remove 3 electrons. So it is a monoelectronic ion and the formula can be used. The N value is equal to 5 and Z value is equal to 4. We are going to plug in these values in the equation for Rn, which is Rn is equal to N square over Z times 52.9 picometers. Solving for it, we end up getting 331 picometers. Let us do another example. Which of the following will have same radius as the second orbit of hydrogen atom? The options given are second orbit of helium plus ion, third orbit of lithium 2+ ion, second orbit of lithium plus ion, and fourth orbit of beryllium 3+ ion. First, I am going to calculate the radius of second orbit of hydrogen atom. For this, the N value is equals to 2 and Z value is equals to 1. If we plug in these values into the Rn equation, we get 2 square over 1 times 52.9 picometers. I'm not going to calculate the final answer yet. So if we just look at this equation, the multiple before the 52.9 picometer is 4. We can calculate this multiple for all the 4 options and see which one gives a value of 4. For the first option, which is second orbit of helium plus ion, the N value is 2 and the Z value is also 2. If we calculate the multiple, you would end up getting 2 square over 2, that comes out to be 2. For the third orbit of lithium 2+, N is equals to 3 and Z is equals to 3. The multiple comes out to be 3. For the second orbit of lithium plus ion, if you calculate that, lithium plus is not a monoelectronic ion, so we cannot use the formula. So we will move on to the next option. For the fourth orbit of beryllium 3+, the N value is 4 and Z value is 4. The multiple comes out to be 4. So the correct answer is option 4. Niels Bohr also calculated the energy of each orbit using the same principles and assumptions he made while calculating the radius. When an electron is in a particular orbit, it has the energy equivalent to that orbit, and the electron does not lose or gain energy as long as it is in a specific orbit. He called these orbits energy levels. According to Niels Bohr, energy of nth orbit En is equals to negative 13.6 times Z square over N square electron volt. Electron volt is a unit of energy and 1 electron volt is equal to 1.602 times 10 to the negative 19 joules. So we can calculate the value of En in joules by using the conversion factor. En is equal to negative 13.6 Z square over N square electron volt. We are going to multiply this number with a conversion factor that cancels the electron volts and introduces joules. So the conversion factor is 1.602 times 10 to the negative 19 joules per 1 electron volt. The electron volt and electron volt get cancelled. If we plug in these values into a calculator, we get En is equals to negative 2.178 times 10 to the negative 18 Z square over N square joules. Let us do a few examples to get a hang of this formula. Example 1. Calculate the energy of an electron in the first orbit of a hydrogen atom. According to formula, energy of the nth orbit En is equal to minus 2.178 times 10 to the negative 18 times z square over n square joules, where z is the atomic number and n is the orbit number. For the first orbit of hydrogen atom, z is equals to 1 and n is equals to 1. Plugging the values into the formula, we get E1 is equal to minus 2.178 times 10 to the negative 18 times 1 square over 1 square joules. You would end up getting minus 2.178 times 10 to the negative 18 joules. You can do a similar calculation in electron volts and you would end up getting minus 13.6 electron volts. Let us do one more. Calculate the energy of an electron in the second orbit of a hydrogen atom. For the second orbit of the hydrogen atom, Z is equals to 1 and N is equals to 2. Plugging the values into the formula, we get E2 is equal to minus 2.178 times 10 to the negative 18 times 1 square over 2 square joules. So the energy is 1/4 of the energy of the first orbit electron. It comes out to be minus 0.5445 times 10 to the minus 18 joules, or minus 3.4 electron volts. If we continue to do this, we get for E3 minus 0.242 times 10 to the minus 18 joules, or minus 1.51 electron volts. E4 is minus 0.136 times 10 to the negative 18 joules, or minus 0.85 electron volts, and so on. Let us calculate one more orbit's energy in the next slide. Calculate the energy of an electron in an orbit with n is equals to infinity in a hydrogen atom. For a hydrogen atom with n is equals to infinity and z is equals to 1, what it means is the electron is outside the atom and it is not influenced by the nucleus anymore. So E infinity is equals to minus 2.178 times 10 to the minus 18 times 1 square over infinity joules. You would end up getting 0 joules or 0 electron volts. There are three important points to note here. 1. The electrons in the orbits have negative energy. What does that really mean? The energies of electrons in an orbit are assigned values in reference to the energy of a free electron. As we have calculated earlier, a free electron, that is an electron not bound to a nucleus, has energy equivalent to 0 joules or 0 electron volts. And the energy values of electron bound to a nucleus are calculated relative to the energy of free electron. For example, electron in orbit 1 has 2.178 times 10 to the minus 18 joules of energy, lower than that of a free electron, and for an electron 2 in orbit 2, it has 0.5445 times 10 to the minus 18 joules, lower than that of a free electron. Point number 2. As we have seen in point number 1, electron with a negative energy means it is bound to the nucleus. The more closer an electron is to the nucleus, we say the more bound it is to the nucleus, and the smaller is its energy value. In terms of magnitude, its value is higher, but the negative sign in front makes it smaller. Therefore, we can say that E1 is less than E2, less than E3, and so on. The third important point is about the spacing between the energy levels. The spacing between these energy levels, just like the radius, are not equally spaced. The spacing between the E1 and E2 is more than that of spacing between E2 and E3, which is more than that of E3 and E4, and so on. As the n value increases, the spacing between the energy levels decrease, and the energy levels get closer to each other. If we plot these energies, we obtain the following graph. As we can see, the energy gap between the levels keep decreasing with n value. The last postulate of Bohr's model of atom. When an electron jumps from lower orbit to a higher orbit, it absorbs energy, and when an electron jumps from a higher orbit to lower orbit, it releases energy. The energy absorbed or released is equal to the difference in the energy between the final and initial energy levels. Delta E is equal to E final minus E initial, where delta E is the energy absorbed or released, E final is the energy of the final level, and E initial is the energy of initial energy level. This postulate explains what happens inside an atom when an emission or absorption spectrum is recorded. When we shine light on an atom, we said that an atom absorbs energy and gets excited. As a result of this absorbed energy, an electron inside the atom jumps from a lower energy level to a higher energy level. For an emission spectrum, we said that the excited atoms, which are unstable, release energy and come back to the ground state. This released energy is a result of an electron jump from a higher energy level to a lower energy level inside the atom. This also explains why the absorption and emission spectrum of an atom are photographic negative to each other. For example, in the absorption spectrum, an electron absorbs a photon and jumps from E1 to E3. The energy absorbed can be calculated by the formula delta E is equals to E final minus E initial, that is E3 minus E1. Because we are subtracting a smaller value from a bigger value, we get a positive value for the delta E. The positive value for delta E means that the energy is absorbed or a photon is absorbed. Because of its high energy, the electron in a higher energy level is unstable. So, it jumps back to the lower energy level. When an electron jumps from E3 back to E1, the energy released can be calculated as delta E is equal to E1 minus E3. Because we are subtracting a larger number from a smaller number, we get a negative value for delta E, which means a photon is released. The energy of the photon, however, in both cases is equal to the modulus of E1 minus E3. That is, the same photon that is missing or absorbed in the absorption spectrum is released in the emission spectrum. Let us do one example problem to wrap up the Bohr's model of hydrogen atom. An electron in a hydrogen atom jumps from n is equal to 4 to n is equals to 2. Find the energy, frequency, and wavelength of the emitted photon. It's given that the electron jumps from n is equals to 4 to n is equals to 2. And we know that the energy of fourth level is greater than energy of the second level. The energy released during this process, delta E, can be calculated by using the formula delta E is equal to E final minus E initial, that is E2 minus E4. In the earlier slides, we calculated E2 and E4 values for the hydrogen atom. Plugging in those values into the delta E equation, we get delta E is equals to minus 0.5445 times 10 to the minus 18 joules minus of minus 0.136 times 10 to the minus 18 joules. The delta E comes out to be negative 0.4085 times 10 to the minus 18 joules. The negative sign suggests that the atom has lost energy in the form of a photon. Energy of the photon is equals to modulus of delta E, that is positive 0.4085 times 10 to the minus 18 joules. We know that the energy of the photon is equals to h times the frequency of the photon. Dividing both sides with h, we get the frequency of photon is equal to energy of the photon divided by h, the Planck's constant. Plugging in the values, we get 0.4085 times 10 to the minus 18 joules divided by 6.626 times 10 to the negative 34 joules second. Joules get cancelled, and the frequency of the photon calculated is equal to 6.17 times 10 to the 14 second inverse or hertz. Keep in mind that since the units of Planck's constant are in joules second, we use En values in joules instead of electron volts. For the third part of the question, we need to calculate wavelength. We know that wavelength times frequency of any particular electromagnetic radiation is equal to the velocity of that radiation. So lambda is equals to velocity of the electromagnetic radiation divided by frequency. That is 3.00 times 10 to the 8 meter per second divided by 6.17 times 10 to the 14 second inverse. The second inverse get cancelled, and you would end up getting 4.87 times 10 to the minus 7 meters. If we convert this into nanometers, we get 487 nanometers. This wavelength lies in the visible region of electromagnetic spectrum.